So, as we've been going through this data set, the P's example, which is something that we worked out by hand when we were learning how to do an Anova, it might seem to you that the way we've gone through it is a little bit chaotic. And it is a little bit chaotic because I'm trying to teach you skills as we go. So this is kind of how I go through any data set. The first thing that you want to do is you want to read in the data set, and then you want to check it for errors. And so you want to look at the data set, you want to check its structure, et cetera, et cetera. That may take a number of steps in R, so each of these things may take a number of steps, but by the end of this step here, you should be assured that R read in the data correctly, the data that you got from the researcher is correct and free of errors, et cetera, et cetera. Sometimes checking for errors requires that you visualize it so that you can look for outliers that might be miskeyed data entry. When I have my research students do data, they hate it because I make them enter the data twice and then they compare columns to one another to search out errors. And we inevitably find keystroking errors where you just made a mistake while you were entering the data. Once you feel confident that your data is free, then you need to test the assumptions. The main two assumptions we're going to be testing is normality and homogeneity of variances. If you find that those are in violation, then you might need to transform the data. If you transform the data, you have to then retest those things and make sure that the transformed data actually alleviated that violation of the assumptions. Once you have data that meet the assumptions, you need to run the statistical analyses, you need to conduct any post hoc tests, you need to create meaningful graphics. If you did a data transformation over here, that means that you'll also be back transforming your data. And then the last thing that you have to do is you have to translate your findings into language that a normal human being will understand. And sometimes this is the challenge, but that's part of what writing a report is about for you guys. So what we did is we read in the data, we checked for errors, we tested the assumptions, we found that we violated the homogeneity of variances assumption, so we transformed it. In the process of doing this, we did some visualization, which is the kind of visualization that we would do at the end, because we had this transformation that kind of reversed the order in which the treatments were in terms of their magnitude. The fastest growing group ended up being the lowest number in the transformed data. So now we've kind of taken a break. We haven't gotten back to running the analysis and doing post hoc tests because we're still working on this section here, simply because I wanted you to see what the effect of the transformation was. I wouldn't normally do it in this order. So as soon as we finish back transforming the data and recreating a new graphic, we'll go back and we'll rerun the Anova and remind ourselves what the Anova said. I'll show you how to run post hoc tests in R, and then we will have completed P's analysis. And hopefully we'll be done with all of that by the end of today. Yeah.
Question, when we found that it violated the homogeneity of variances rule, did we run a Levine's test to see that?
After we transformed it or before we transformed it?
Before we transformed it.
Yeah, we did. Yes, it's in there. Where is it? It is in my section. It is after this. Oh, that's the transformed data. That's the transformed data. Yeah, right here we did it. I'll just rerun that.
Okay. And what do we get as our output there?
We got a significant result.
A p-value is greater than
Is less than 0.05, yeah. Which means that at least one of the variances is different from the other variances. And that's why we went through all this rigmarole of transforming the data that then means we have to back transform the data when we go to make graphics.
Okay, thank you.
Yeah. And then what we did was we did the transformation. Here's the transformation. So here's where we tested the homogeneity variances. Once we tested it, we found that it was not correct, so then we transformed the data. Then we reran the transformed data again, and we found that the Levine's test is now not significant, because greater than 0.05 for a p-value. So that transformation worked. It's a really weird, unusual, arcane transformation. it is not one of the usual transformations. If when you start working on your data sets for the written portions, do not try and apply this transformation to that data set. It will just mess it up even more. If you find that you need to transform the data, go to your textbook, which talks about data transformations. If you have certain problems with your data, try this transformation. If you have other problems with your data, try this transformation. If your textbook doesn't help you out, then come and talk to me. If it's a deviation from normality, have you guys looked at the data set at all? If it's a deviation from normality, do you have to be all that worried about it? No? Yes?
I was gonna say, don't we have a huge sample size that?
In this case, we actually have really big sample sizes for the most part.
Yeah.
And so if you have a large enough sample size, you don't really have to worry about the normality assumption because central limit theorem. Central limit theorem saves your butt because you're making inferences about means, and what does the central limit theorem say about the distribution of sample means?
It's always normal.
If you sample from it over and over again, the distribution of sample means is normally distributed regardless of the shape of the underlying distribution you're drawing those means from. So once you reach 20 to 30 in terms of sample size, you don't really have to worry that much about deviations from normality. The really important one that bites everybody in the butt is the homogeneity of variances assumption. If you violate the homogeneity of variances assumption, you have to look really carefully at your data to see kind of how far apart the distributions themselves are in terms of whether or not you can rely on that, whether you need to worry about that. So let me just go and get the data for you again. No, that is not the right file. So here's what these data look like. So the first thing that I'm having you do for this project is I'm having you actually analyze body temperature data. And the body temperature data are divided up by season, and they're divided up by locality, either Galveston or Edmond, Oklahoma. Now, one of the things that you'll probably notice when you go to graph the body temperature data, which is just this one little section, is it appears that there are differences between the two populations in winter, and there are no differences between the two populations in summer. Those two distributions overlap a lot. What you'll also notice is that in the winter, it seems like the variation, especially in Galveston, is higher than the variation either in either population during the summer or in Edmond, Oklahoma in the winter. And so you're going to run a test on the homogeneity of variances, and what you're going to find is that no transformation that you attempt that is recommended for stabilizing variances actually stabilizes the variances. How do I know this? Well, I've already analyzed the data. So you're going to encounter that. You're going to get a violation of the homogeneity of variances, and nothing you do is going to fix it. Is it a problem that we really need to worry about in this data set, though? Why or why not? Looking at this panel right here, which is body temperature. Karis, ideas?
I think it's because, I could be wrong, but it's because neither mean is included in.
But that's the problem. That's actually the problem with violating the homogeneity of variances, is when we think about a test of means being different as being a test of inclusion, if you have two means, one of them has a really wide variance, one of them has a really narrow variance, this one is included in the confidence interval of this one is not included in the confidence interval of this one, so are they different or are they not? It's ambiguous. What's nice about this particular situation?
I'm saying we don't have any of that.
We don't have any of that. Those two distributions, even if they have different variances, they're both pretty far apart in the winter, aren't they? And so even though this variance is higher than this variance, and this variance is actually higher than either of these variances, none of these things are close enough together that we're really confronted with this issue.
So we don't have to transform our data.
So what I would do if I was doing this is I would say, okay, we violated one of the assumptions, but then I would show a graph of the actual data and say, but because the distributions of the data are such that the distributions themselves don't really overlap with one another very much, that's not really an assumption that we have to worry about violating. Even if violating the assumption reduces our ability to come to the right decision, because of the distribution of these particular data, it's probably not going to be much of a problem. And so there is a certain degree of statistical judgment. One of the things that I tell you to do over and over again as you're going through this process, visualize things. Visualize the data, because when you get to this homogeneity of variances assumption, you have to figure out, is that something that I really need to worry about and spend a lot of time on, or is it something that I can effectively ignore simply because of the structure of the data? Yeah, you had another
As we
question.
say, are we treating the location as the treatment or the time of year?
So in your instructions, it's a combination of location slash season. So you'll actually have 4 different treatments, so to speak.
Oh, okay.
You'll have Edmond, Oklahoma, summer, Edmond, Oklahoma, winter, Galveston, summer, and Galveston, winter.
Right, okay.
Because all you have available to you in your toolkit right now is a one-way analysis of variance.
Right.
So you're basically testing to see, is this different from that? 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 And are these two different? And so what we've done is we've conflated location and season into one variable. This is something that you see people do periodically because they don't know anything other than a one-way ANOVA. The next assignment that you get, we're actually going to learn how we tease those two things apart. So we can look at location separately from season. We can test to see if there's an effective location. We can test to see if there's an effective season, and we can test to see if those two things interact with one another.
Okay.
And that's what we started doing on Friday.
Perfect.
So yeah, and when we learn how to tease these two things apart, the same method that we use for teasing two things apart will actually allow us to analyze this whole thing. So we'll be able to not only tell if the locations are different, we'll be able to tell whether the seasons are different. We'll also be able to tell if these different types of temperature measurements are different from one another. So we'll be able to say, is winter different from summer? Is Galveston different from Edmond, Oklahoma? And we'll be able to say, are environmental temperatures different from wall temperatures, different from body temperatures, different from preferred temperatures? And that's actually a 3-way ANOVA, but the same method that we use for doing a 2-way ANOVA can be expanded to a 3-way ANOVA or a 4-way ANOVA or a 5-way ANOVA or a 10-way ANOVA if you felt that crazy. Once you have the one tool, that tool can be expanded to as many different axes of data as you can possibly imagine. Better to not have too many different axes of variation, because then interpretation becomes a little tricky. But we can actually analyze this whole data set once we learn the thing that we're going to start learning on Friday. Does that help? Okay. All right, so let's go back to, everybody hopefully has run their R script up to the point that we ended off last time. So let's just try and take this, whoa, where am I? We now have this this new data frame that has the transformed data and all of the back transformations in it. And I've called mine CI-plot trans. And so let's look at that again, just to make sure that we remind ourselves what it looks like. And in this case, what I've got is I've got the control 2% glucose, 2% fructose, the 1-to-1 ratio, and the 2% sucrose. I've got the sample size. I've got the mean of the transformed data. I've got the confidence interval of the transformed data, and then I back transformed this mean into the original growth increments. Then I got the upper limit based on transforming the confidence interval and adding it to the growth increment or subtracting it from the growth increment. So let's see if we can just copy the last graph that we made, copy that graphic block, paste it down underneath this, and let's see if we can just use this new data frame to plot the data. So what I've done is I've created myself a new code chunk here for plotting the back transform data. So let's go up and get the most recent graph that we made, which was t-graph. So copy all of t-graph and just plunk it in here, and then we'll start messing with it. So put your blue sticky up when you've got t-graph copied into this new code chunk. Don't mess with it yet, just get it copied. You don't have to type it in, you just have to go and find it and then copy it and paste it in. So you got it done. Recent graph. Well, you could use t-graph or a graph, it doesn't really matter. We're going to change the name of it anyway. You don't need to CI plot because we're going to be using the confidence interval data frame we've been working on. All you need is the graph and block. Yep. Okay. There you go. Okay. Don't worry. Let me see your graph and block. Did you run everything? Did you run? Show me what X looks like. Run X. Oh, runs out of block. Oh, you've got a bunch of nulls. Did you load in your data files and everything from the beginning? Okay. Just run the single line of X. Just put your cursor there, run command enter. Oh, it gives you that. Okay, so you do have that. So go back to the whole graph. So run the graph and then go run that. Now ask for what ask for. Oh, whoa. That's weird. All right, go back up to the graph. You don't have pluses at the end of any of your lines, so it's not including anything after that first line. After every line, yep. Because that plus takes you to the next line. Yep. Now run that again once you've got all that done. Yeah. Yep. Yeah, you can run some jump. You can also just run the graph. So do this because that's not saved yet. So run this. Oh, we have to save it. Oh, get rid of that plus. Yeah, 'cause that finishes the code block.
Yeah,
This is
yeah.
just your massive part. Yep. Now, we'll stinker. All right. Go back up here. Jump. start asking yourself how you need to alter this graphing block in order to accommodate the new data set that you have. We're going to have to make some changes to it while I'm trying to figure out what's going on. Sometimes it's just running little sections. So let's see. So one of the ways you can check your code is just by showing it with the next line. That's weird. Okay. So now let's go. That's yeah, so something's happening. Change all those things. We're still doing it. So what is happening? Let's do this. Actually get rid of the background. I should get rid of the grid lines. Okay, so what's the deal? So let's run this whole thing. No, let's run it. Okay, I don't know what the deal is. All right, so copy that and paste it around. All right. Yes, ma'am. Yeah. Yep. Yeah. All those formatting things we want to keep. Actually, I'm going to show you a trick about that in a little while, but yeah, we want all that. All right. Tabs down. So we have this new graphing block. So let's rename this graph something like final graph, because that's going to be our final graph. We're still dealing with the CI plot trans data frame. We still want treatment to be the thing that we're graphing, but do we want transdat to be the figure that the data that we're graphing, or do we want to be graphing something else? No, we want to be graphing what? We want to be graphing growth. And if you want to remember what the data frame looks like, it's right down here. We want to be graphing growth. And then is the minimum going to be transdat minus the confidence interval?
No.
What is it going to be?
CI plot trans LL.
Is that what I named it? I only named mine LL. So whatever you named your lower limit, that should be what you put in there. And then whatever you named your upper limit should be what you put in here. One of the things that I like to do when I'm checking to see if code is running correctly is I'll just run the lines that I finished tinkering with So in this case, what we did was we changed the variable that we're plotting and the confidence intervals around those means. So I want to run the first line, the second line that plots the error bars, and the third line that plots the means, just to give us a little check to see if the changes we made are actually taking hold. So run that, and it looks like it worked, because now our control is the highest mean, 2% sucrose is the next highest mean, and then these three means are all down here. So it looks like we changed the graph so that it is now reporting the back transformed data. Is this now the growth increment of p's still? It is the growth increment of p's, right? It's just the back transformed growth increment of p's. Is the growth still expressed in millimeters? It is expressed in millimeters now. It's not expressed in those wacky transformed data that we had before. Is treatment still treatment? Are these still the treatments? Yes, they are. So nothing else has changed. So now we can go down here and change our call code where we're going to ask it to produce it. So we can now just run final graph and then get it to give us the final graph. And what we should see is a final graph that looks like this. Blue tabs or green tabs up when you have this completed successfully. What happened there?
Yeah, that's why that's
Because you still have y as transdat. You
Oh,
didn't change transdat to growth. So it's plotting your means for your transform data, and it's putting your confidence intervals up where they actually
Okay.
belong. Yep. Okay. So what happened? So all it's okay, and that's what that is. Okay, so now run the whole thing. Go up here just to the final graph. Just put it anywhere in there, and it can be a picture. All right, so it looks like. Okay, so let's go to title. Just comment out title for the hashtag in Francis.
Yeah, just choose.
Hashtag. Now run it again. What you can do is just commented that out so it's like one of those two lines. So I was doing this earlier. So one of the things that's nice to do is just, so we did this and it ran, right? So let's go ahead and put this back. And oops. What we should see over here is we should see that. Oh, we lost a plus here. Yeah, that's right. Boom, boom. Yeah. Always check for pluses at the end of your lines to make sure that you didn't accidentally delete a plus when you were going through this. So let's go back and look at my plotting block here. So I was just working with Elizabeth's thing, and she just somehow inadvertently got rid of a plus value there. We can actually go back and resurrect Karis's scaling thing here, and if you get rid of that plus, it basically doesn't continue on to the next line of your code, and so you won't get the rest of the code for the plot running. So we've created a meaningful graphic. It has means, it has confidence intervals, and more importantly, the transform data were what you analyzed, but you're viewing the result using the back transform data. And so it's presented in units that the researcher who was working on this project will actually understand what the heck is going on. Now, we have now created how many plotting blocks? Let's see. Well, we can go to our our thing here. We have made an untransformed data plot. We've back transformed the data and made a new plot. So we've got a couple of different plotting blocks. We've got 1, 2. We've got 3 plotting blocks, and one of the things that we've been doing all through this time period is we've just been copying blocks of code that make a plot, pasting them into a new place, and then altering the things that need to be done. Rachel just asked me a few minutes ago about this theme block here. One of the things that I like to do, and you'll see this in the R markdown for the P's analysis that is on the Moodle site, one of the things that I like to do is to create a theme at the very beginning of a project, and then I save that. So let's do that. So let's go down to this last block that you were just working on. And what I want you to do is go up to the top of this block and give yourself a couple of spaces of a couple of lines, and put in a comment. And the comment should say something like, create a common theme. And what I want you to do is I want you to type in TH, and then give yourself an assignment operator, and then I want you to go down to whatever your formatting things have been down at the bottom, regardless of how elaborate they are. Mine are fairly elaborate because I like changing every little thing about a graph to make it look the way I want it to look. Copy that and plunk it in up here, and then run that. Blue tab's up when you've got that accomplished. I think we fixed it, right? Yeah. All we're really doing is we're saying, whenever I type the letters TH, I want R to do all of this. Just put it anywhere in there. It doesn't matter. It's all connected. Just yeah, looks like you're fine. Recording's still working. Oh yeah, no, make sure, sorry, you didn't follow instructions. Yeah, that's the problem. It's trying to run this is part of a code, graph. This will run. Do you have ggplot loaded?
Yeah, I had it up here. Scroll down.
on with somebody else. And you need to make an appointment with me to come by and get that straightened out. All right. So everybody's done this? Everybody wake back up. Sorry about that. Type in TH here, and what it should return is it just should return to you what you had typed in before, except it's going to have a bunch of other stuff associated with it. But it's basically a bunch of formatting stuff. So it's asking you for, it's basically telling you for subtitle, you didn't have anything for subtitle, so it's just got a bunch of null stuff in there. But what I want you to do now is go back down to your block of graphic code that you just did, and I want you to delete all of that that's there and the plus sign at the end of scale x discrete. What you're basically removing is you're removing all of the formatting and rerun that block of code and look at what your graph looks like. It should revert back to this ugly, hideous thing that we started with earlier. Yeah, everybody's tabs can come down. Now what I want you to do is go back and put the plus in. Yeah?
Mine didn't do that.
Yours didn't do that. Let me see. Okay. Okay. Did you run it and then ask for it? You didn't ask for it. Make sure you ask for it after you run it. Oh yeah, there we go. Yeah. Everybody else get this? Yeah. Okay, so let me see what we did. Wait, that's just running one line. Oh,
Oh, I thought that's what you wanted.
no, I want this whole thing.
Just the whole thing right here?
Yes. Well, yeah, well, that's doing everything. Go for it. All right. We're running it toward the right.
Yeah.
Now that's working. Okay, anybody else have any difficulties? All right. Okay. So what you have is you have this graph that's not formatted. So at the end of your last line of your graphing code, put a plus, and then on the next line just type in TH. What that does is it tells ggplot to go up and get that theme that you've created and add it to your graph. And when you do, you should get the final formatted graph. Why do I want, yeah, any issues? Who has issues? Yours works? Does yours work? Everybody work? Why is it a good idea to do this?
You have the same thing for all the graphs.
If you have a project that you're working on that has lots of figures, you can make one thematic set of commands that then makes all your graphs look exactly alike. They're the same font. What's that?
I'm saying like uniformity.
It's just uniformity. Everything has the same font sizes. And if you find that your font sizes are too small or too big, you change it once in the theme statement, and then that populates through everything else because you're always referencing back that original theme statement. It's so much faster to just change it at one time and have it populate through the whole thing than if you go to each graphing block and change font size or font style or whatever it is. And so I almost always have one of these theme statements at the top of my script basically saying, this is the theme that goes for every graph in this particular script. And then if I ever need to alter something, I alter in that one, rerun it, and it just makes all of the other graphs in the thing do what they're supposed to do. Did that not work?
Yeah.
Oh, okay, it did. Okay, good. All right. So that's just a huge headache and time saver. It's just one of the things that you learn after a while. And you can do this with lots of things. So for example, and this is another way that you can build up graphs. I'm gonna get rid of stuff at the beginning of this just to show you kind of how this works. I'm gonna copy this. Well, actually, no. I'm gonna call this graph X, even though I've already used that in this script. And I'm going to say, I'm going to copy this first line, and I'm going to plunk it down here at the bottom. Don't do this, I'm just going to show you something. So if I have this one line of code, I have really everything that I need. Whoa, what happened there? Oh, I have a non-matching parentheses. So I have everything I need. If I want to know what X is, I can just, well, crud, hold on. When I do this, when I just have X being this first line of the graph, all it really tells me about is what the axes are. It doesn't plot any data or anything else. But now I can go X plus, and I can add the error bars to it. So I can copy the error bars and plunk them down there. And when I do that and ask for X again, it gives me X with error bars. And so you can actually just say X is, use the assignment operator, X is X plus error bars, and then X is the error bars. And then if you want to add the points to it, you just put the points in here. So what these plus signs do is they're just adding things to the graph that you have. And there you have the points. So if you finish a graph and you want to add something to it, you don't have to go back and recreate that whole graph. You can just take that graph's name, add the new thing to it, and it'll just add that to the graphic block. And so it's a way of tinkering with graphics where you can explore things without altering, once again, the fundamental structure of your graph. I'm going to erase all of this that I just did and put this back as final graph because I want this to be my final graph. And I'm going to run that and make sure that I didn't screw things up, and it runs, and then I'm gonna delete the rest of this stuff. Okay, questions about messing around with graphics. What might it also be useful to have on this figure?
You said you're not a big fan of grid lines?
I'm not, but you can be. It's a stylistic choice for me. And when I grade your papers, I separate style from substance. Would it be nice to know which of these treatments is different from which other treatments? Sure. The way you oftentimes see this done is people will put letters above each of these things. If two things have different letters, they're different. If things have the same letter, they're not different. And so you could go in and add letters to the top of this. I won't show you how to do that here, but if you go and look at our markdown file that is on the Moodle site, go to the final graph in that, and you'll see that there's a line of code that adds the letters to the, it puts them right above the error bars on each of these things. So you can easily just copy that script. At this point though, do we know which treatments are different from which treatments?
No.
We don't, because we have not run post hoc tests, have we? So we're gonna make a new R chunk. We're going to rerun the overall Anova on the transformed data and run the Tukey Kramer test. Okay? So how do we run the overall Anova? We have this saved somewhere, don't we? Right? If you'll remember, our first analysis was the untransformed data. Our second analysis was the transformed data. So let's run that. And what we should see is that the formula is here. It has transdat, the transformed data, and the treatment running it out of the data frame dat. Put up your blue tab if that worked for you. Or your green tab if you have a green tab.
Scroll down.
Oh, what do you need?
Just the code, because I already see the code.
Oh yeah, sorry.
Oh, okay.
It's just the name of whatever you called your analysis when you did the transformed data. I called mine analysis 2 because analysis was the untransformed data. Is this a particularly useful way of getting it to display the results of the Anova?
No.
No. How can we give ourselves a more useful output? Use summary analysis 2, and that gives us an actual Anova table, which is kind of what you're already familiar with looking at because you've seen Anova tables before. So we know that there's a difference here because we have a significant overall Anova, and it's very significant. So then how do we find out whether or not differences exist and what those differences are? What kind of test are we going to run? So just type in Tukey and see if it gives you an autofill thing. And it does. It gives you Tukey HSD. You can click on Tukey HSD and do that on analysis 2.
Wait, isn't analysis to our transformed data?
It is. That's what you want to run your Tukey's analysis
Our
on.
back transformed data?
Nope.
Okay.
Because remember, the original data is the data that are homogeneous in terms, or heterogeneous in terms of their variances, and so you want to use homogeneous variance data.
Okay, not the back transformed.
Not the back transform data. Nope. So here you have a table of output. Put your blue tab up if you got this table of output. You just took your blue tab down. Okay, all right. Okay, all right. Show me some blue tabs. All right, good. So what does this tell you? It basically says if you're looking at control versus 2% glucose, it's different. Why is it different? Well, because the p-value is way less than 0.05. Control is different from fructose. Control is different from the 1-to-1 mixture. Control is different from sucrose because all of those p-values are below 0.05. The next one that is below 0.5 is sucrose is different from glucose. Sucrose is different from fructose. Sucrose is different from the 1-to-1. So these three here, all the rest of those comparisons are not different, and those are all of the comparisons between the simple sugars. And so the Tukey's test tells you exactly what the figure tells you. Glucose is different from everything. Sucrose is different from these three, and these three are not different from one another. So your Tukey's analysis should give you the same kind of information that your figure is giving you. Karis.
Quick question. So wait, where do we see which ones are different from which ones?
It's
Sorry.
listed over here, so this is the comparison. Glucose minus control, different. Fructose minus control, different. Well, the 1-to-1 mixture minus
Wait.
control, different.
Oh, wait, okay.
Yeah.
It gives you a p-value like.
Gives you a p-value just like that if you were running an Anova.
So you're looking at less than 0.05 here. Okay.
Yep,
Okay.
yep. So this tells you what comparison, and this tells you whether it's different.
Right, okay.
Yep.
Thank you.
And so that's how you run a Tukey's test. It's really simple, really easy. It doesn't tell you what the minimum significant difference is, but you don't need to know that because it's doing all of the calculations for you. Questions? All right, blue tabs, things that went well. Orange tabs, things that didn't go well. Cole, you're making an appointment with me at some point to